Hi guys, I just got rid of Professor Rigobot, so now I'm gonna be explaining to all of you the network of neurons and the trees of decision, baby. I'm gonna explain it, not a loser.
No, isn't it neural networks and decision trees?
Man, how you got here?
I have been always here.
Wow, that was fast. That was super fast.
No.
Man, I don't know what to do now.
Well,
I feel like kind of weird. Well, before we start, my brother, can I ask a personal question?
yes, you can ask a personal question.
Yes, my friend, my personal question is, let me preface this a little bit. So, I am really concerned about all the lies that you have been telling
No, I am
me.
not telling you.
This thing that you did not suffer an accident.
No.
And a genetic accident is actually not credible at all.
I
just wanted to let you know. Not credible.
Well, I
Not credible,
don't
my
know what
friend.
you think. Why?
So, I was thinking about a test. We're in econometrics after all, baby. So, I was thinking about a test. So, I wanted to ask you several questions to see if it's you or it's me. Okay? I hope you don't mind asking you this personal question, and I hope you don't take it personally.
I'm not going to take it personally. Go.
Okay. So, do we have kids, baby? Do we
Yes.
have kids?
Three marvelous kids.
Wow.
Yeah, they're great.
Wow.
Yeah. Smart.
Wow,
They're all
man.
graduated. Really
I'm so
great
glad
kids.
we have three
Yeah.
kids. Wow, they're great.
Yes.
They sound like they're great, huh?
Yes,
So
they're great.
Let me ask you this question.
Yes.
Are they handsome, smart like me, or are they horrible like you? Okay, can you explain?
No.
What do you mean? It's
No, that's a fair question.
Totally fair question.
No, it's not
Are the
fair.
kids, they look like me? Do they have hair? Are they cool? Are they smart? Are they charming? Or they look like you, like a total loser?
But how can I answer that
What do
question?
you mean? Of course I can answer this question. It's a totally valid question.
No, it's not
Are
valid.
They do look smart like me or dumb like you?
Oh my God. I don't know. I cannot answer that question.
If you don't want to answer the question, then I don't know what is the point of saying, do you mind asking you a personal question, and you saying yes. Okay.
They look like you. They
I'm so
look like
glad
you.
They look like me. So
Yeah.
you see, then you must be the act of an accident because my genes were passed to my kids. Well, our kids.
Yeah, our
and
kids.
those kids are now beautiful, smart, with hair, baby, with hair, and they don't look like you. So you must be the accident of some weird experiment that took place in the 90s that created this weird thing that we have here. Okay? So
No.
that's a randomized control trial, baby. What do you mean?
No, not randomized
Well,
control
we don't know
trial.
what trial they did on you, but if that was a trial, this is the example of a randomized control trial. You see, before and after. Before and after.
No.
Unfortunately, we were selected at random and we were given this horrible drug that produced this horrible outcome that we have here. I mean, I don't know what to tell you, my friend. You should have said no to that experiment.
There was no
Of
experiment.
course it was an experiment.
No.
So, why don't we start with the network of neurons?
Neural networks, the other way.
Okay.
So we're going to start with this set with three videos. The first one is about the general aspect of machine learning. The second one is about neural networks. And the third one is about decision trees. Let me start with machine learning first. What are the components of machine learning in general? Is that machine learning is a set of procedures that create and estimate models and interpret or predict the data. And the idea is that we have a data that where we start, which is called X, that runs through an algorithm, and that algorithm produces an output Y. And there are different ways in which the Y is constructed. So after all, this is in the end an approximation. We're approximating the characteristics of the data X with the algorithm to explain Y. And again, it's the same idea of the regular econometrics, where the algorithm is the auxiliary model. Okay, so this started a long time ago. It started on something that was called control theory and optimization. At that time, it was mostly theoretical. The computers were incredibly slow. I do remember they were incredibly slow at the time. And yes, they were incredibly slow. And the computers just got much faster. They got faster and they got closer to the math. And that's why today we have such an incredible revolution. So in fact, they changed the name. Control theory at that time was mostly to control gates in a river, for example, to control the flow of water. And that's what we used to do at that time. Then when the computer started to get better, we created all these optimization tools, and now we call them machine learning and artificial intelligence. Okay, so that's where we are going. There are three types of machine learning. One is called supervised learning, unsupervised learning, and reinforcement learning. The differences are subtle, but I would like to highlight. So in the supervised learning, we have a variable y that is the one that we want to somehow predict or track or forecast, and we express that as a function of the data of the x's. And the function can be parametric or non-parametric. They tend to be very complex and very flexible, but the idea is that we want to use the data that we observe to try to predict something about the y. Unsupervised learning is that there's no y. So we are only going to characterize the x's and the properties of the data by themselves. And reinforcement learning is that we might have a target y where we want to kind of predict or forecast or reproduce. It's just that an outsider gives us the loss function that tells us, you did a good job or a bad job and how good or how bad the job is. Every machine learning problem has 5 components, okay? The first one is that to understand what the problem is that we would like to understand the mapping from the data to the objective function, okay? So we're gonna call that mapping U. We always have hypotheses that we want to test, so questions that we want to ask to the data, things that we want to learn from the data, and these are a set of restrictions on the F. We have the observed data, and in fact, the observed data, if it's reinforced learning, you will have a y, x1 and y1. If it were just unsupervised learning, it would be like x1 and x1, okay? But we all have a data, and we will define that data D. There's an algorithm that is the one that approximates that function f, that is the mapping between x and y. And we always have a function that it represents the loss or the distance or the accuracy of our predictions. Okay, that metric, which is E, is used in the algorithm to determine how far or how good is the choice of f hat. So these elements are present at all times, similar to the ones that we have in regression analysis. In regression analysis, we have the mapping is linear. The hypothesis testing is that whether or not the coefficients are 0, the data is the data, the algorithm is OLS, and the measurement of error is the residuals that we get from the estimation. So it's very similar, the components are very similar. And in fact, when you think about a linear regression from the machine learning point of view, what we have is a bunch of x's. These are all the regressors, okay? And all those regressors enter a function where they are multiplied by alpha 1, then they're aggregated in a linear form, and we produce y hat. And there's a distance between the f hat and the y hat, and that distance is the measure of the error. When you do neural networks, it's a little bit more complicated because the functions, the algorithms, the functions are what we call activation functions. They are more complicated. But at the end of the day, we have x that enters a bunch of functions. We produce a prediction, the a hat, and we compare that a hat to the y. And therefore, we are going to look at the errors that we will have. So machine learning has 3 problems. One is very easy to overfit, and I will show you an example in which you just change the volatility and the exact same regression, the exact same data just blows up. And so this is a problem. So the overfitting is very simple, and in fact there are many aspects in the data that will lead to overfitting, and it's difficult to tell. Okay, so the second one is the construction of counterfactuals. In general, the idea of the orthogonalization that takes place in OLS is that you can change one variable by keeping everything else constant, and therefore you can truly understand what will be the impact or the marginal impact of one variable on the overall prediction. That cannot be done in neural networks. It's very complicated to actually understand what happens, and therefore there's a bunch of confounding effects that are taking place at the same time, and therefore, in that sense, it will be difficult to do that. For example, you can estimate with multicollinearity without a problem, because the neural network is going to assign 0 to one of the variables, so it's perfectly fine. So this is the complicated aspect, is that when you should not have a counterfactual, you still can construct a counterfactual. And the third problem is extrapolation. So machine learning works really, really well within the data that you're estimating, but might work really bad when you're getting out of the range of that data. By the way, that can also be a problem for any technique if the behavior outside the data changes. But imagine that everything is linear, then estimating in one region is very easy to extrapolate in the other region. That's the beauty. When you do things like decision trees, there will be no decision tree on a part of the data that has not been observed, and therefore there will be no ability to predict. So the extrapolation is a tough one. So let's start with neural networks and decision trees.